Okay, thanks for being here. And it's a pleasure to introduce Lucie Baumont. She has a French name, but she's not French. She's from the US,
yeah.
And but her father is French. That's the reason why she has a French name. And she got her PhD at Stony Brook University. She was working on gravitational lensing of clusters. And after that, on the contrary of Stefano, who took the bad decision, she took the right decision. She came to Cosmostats and she joined for a postdoc our group there in Paris, Saclay. And she's working now with us here with Andreas. And but you're not going to present what you're doing with Andreas, right?
No.
So more on your work during your PhD.
Yeah.
And she's here for the whole week. So if you want to discuss on this subject with her, she's sharing an office with Andreas close to the student office.
Okay, well, thanks for the introduction. I'm going to be talking to you a little bit about galaxy clusters, but I know not everyone comes from a cosmology background, so I'm going to start with some nice cosmology introductions. Also, I'd like to I'm going to be talking about a measurement called fgas, and it's been made with many collaborators, and I have listed them here. So this is just a little overview of what I'll be talking about. I'm going to introduce Lambda CDM, our standard model of cosmology. I will then talk a little bit about galaxy clusters and how different physical processes lead to different signatures across the electromagnetic spectrum. Then I'll talk about actually this fgas measurement, how we can constrain cosmology with it, and then how we actually measure it. And mostly what I do is weak cleansing mass calibration for this measurement. So I will talk in a little bit more detail about weak cleansing mass calibration, and then show some results and some outlook about the future of this measurement. So first, sometimes it's nice to have a very general slide about what cosmology is. Of course, it's the study of the evolution of the universe. And so we follow this cosmological principle. Basically, if you zoom out enough, the universe looks very, very uniform. And so we have this idea of homogeneity and isotropy. So anywhere you look, the universe should be the same. And of course, it doesn't look like that on close scales. But if you zoom out to a scale of about 300 billion light years, or which is equivalent to about 250 megaparsecs, then it is very uniform. And so the universe is very simple once you zoom out far enough. And if you look into the very early universe, you can probe the quantum gravity regime. So people are very interested in saying, well, if we have effects from quantum gravity, do they propagate up towards modern day so that we can see some signature in these very large scales? And so Lambda CDM is the standard model of cosmology, and it is based on general relativity. And so again, with this assumption of a homogeneous and isotropic universe, and it contains matter, which is cold dark matter. So it's dark matter that is just gravitational. And it has a cosmological constant. So that causes the accelerated expansion of the universe. So you can parameterize this model with 6 parameters, which is pretty amazing. You can describe the entire universe in 6 parameters. And so I've listed some different parameters that people use here. The ones that I'll mostly be referring to are the baryonic matter density and the dark matter density here, and perhaps the matter density, which is just the sum of these two, and a little bit of sigma 8, which is matter clustering. And there are some very common extensions to this 6-parameter model that we'll also be discussing a little bit. So one is the dark energy equation of state. W tells you the relationship between pressure and density of dark energy. It's for lambda CDM, the standard model, W equals -1, but you can try to free that up to see if perhaps this equation of state changes, and it's not a cosmological constant, it's something else. So that's one thing we'll look at. Some people add in neutrino masses or additional sterile neutrinos. That's another possibility. Or you can also add curvature. So you can say that the universe is curved and not locally flat. So flat lambda CDM is the standard model of cosmology because it has successfully solved a number of problems. And it has a number of like really resounding successes. And so one is it really describes large scale structure in the distribution of galaxies of the universe. It describes the existence and structure of the cosmic microwave background, and to like amazing precision. They're doing, 4 decimal places. It's very tiny signals that they're able to pick up with this model. It also describes observed abundances of these different elements and the accelerated expansion of the universe. So some basic principles of this model is that the universe expanded from a very, very small region exponentially. And so this allows it to be uniform on very, very large scales that wouldn't be in contact, in causal contact with the speed of light traveling through these different faraway distances. So you have this period of very uniform universe where you have the cosmic microwave background. And then as the universe expands and cools, you start to have the growth of structure. And the other thing you should note about this model is that there's a hierarchical growth of structure. So the universe is very uniform, it expands and cools, you start to get stars, and then they form galaxies, and then they form this last part, galaxy clusters that we'll be studying. So it's very uniform at the beginning, there's hierarchical structure formation, and then also that the universe is accelerating in its expansion due to dark energy. And so that's kind of the principles of lambda CDM and why it's so successful. Flat lambda CDM has some problems though. One is in this model, it calls for dark matter and dark energy, and they make up most of the energy and most of the content of the universe. Actually, they make up 95% of the content of the universe, and we don't understand them. So that's a huge problem. There's some theoretical issues. If you want to put in a cosmological constant into, say, quantum field theory, it requires an infinite number of finely tuned corrections, which might indicate that the theory is broken. So that's a big theoretical issue. We also see issues in data. So there are some light tensions to heavy tensions, depending on who you ask. People look at H0, the expansion rate of the universe. And they find somewhat like a 5 sigma tension between early universe and late universe measurements. So that's an issue. Some people have looked at this growth of structure. And again, between early universe measurements and late universe measurements, they find this maybe 2.5 sigma tension. So, okay, we don't know exactly what the tensions are or if they're due to systematics or not, but we know one thing, and that's we have to make more measurements. So I think we should be very motivated to learn more about lambda CDM because these are all huge problems that we don't understand. So the other thing I wanted to mention is one reason why this particular measurement that I'm about to show you is so nice. So there are many cosmology measurements that people do, especially in regards to that last tension I showed between omega m and sigma 8. And you see a lot of plots like this. This is one from DES collaboration, but everyone has these. And they often plot omega m versus sigma 8. And they see these nice round contours that they can compare to each other, which is great when they're comparing different measurements, their year 1, year 3, whatever. It looks very nice. But actually, sigma 8 is this kind of modified quantity. It's been rescaled. So what you're actually dealing with are these huge degeneracies from a lot of different cosmology measurements. You have these bananas. So the real quantities you're looking at are very degenerate. So if we want to understand this better, we need to find some way to break this degeneracy. And so the measurement I'm going to show you will turn this banana, why can I skip slides, into an apple. So we'll find a way to break this banana degeneracy by having a nice constraint on omega m so that we can actually have a much better look in parameter space. So now that we've learned a little bit about cosmology and some issues with other measurements, we can start to look a little bit at galaxy clusters. So as I mentioned, lambda CDM calls for hierarchical structure formation. So the largest gravitationally bound structures you get are actually galaxy clusters. And they're very, very big. They're the largest virialized objects in the universe. Their mass range is something like 10 to the 14 to 10 to the 16 solar masses. And they're very large across, maybe 2 to 10 megaparsecs across. So this is smaller than a cosmological volume, but under our theories of gravity, these collapsed to form these clusters. Matters collapsed from even larger areas. So it covered cosmological volumes, essentially collapsed gravitationally to form this huge structure. The other thing is there's a number of physical processes that allow us to observe them in different wavelengths. So galaxy clusters, even though they're called galaxy clusters, only contain maybe 2% galaxies. So that would be the sprinkles on this cupcake. So the rest is hot gas. It's accelerating in the potential well of the cluster caused by its huge gravity. And so it emits bremsstrahlung radiation in X-ray. So, and you can see this radiation in X-rays here. This is from Chandra of Able 2029. This X-ray gas also can scatter photons from the CMB, so cosmic microwave background. Photons, they hit this X-ray gas and they hit the particles of this, gas that's accelerating, and they get upscattered. And so if you look in the CMB, this is called the Sunyaev-Zeldovich effect, you can also see tracers of this gas. And so in the optical, you see the galaxies, the sprinkles, and you can see an overdensity of galaxies as you see here. You see them, they tend to be red and dead because galaxies tend to lose star formation in clusters. So this is kind of the physical range of galaxy clusters. The last thing I should mention is most of galaxy clusters are actually dark matter. So it's invisible, but we know it's very heavy. And so through different measurements of the total mass of galaxy clusters, we're able to find that, well, it's not the gas and it's not the galaxies, so it has to be dark matter. So what is this measurement fgas that I am giving this whole talk about? So it's very simple. Fgas is a fraction, and it is just the ratio of the mass of the gas in a galaxy cluster to the total mass of the galaxy cluster. And as I said before, galaxy clusters are really big, so they collapse from even bigger areas of the universe, cosmological volumes. So you can say they are a pretty good sample. If you look at the matter inside them, it should be a pretty good sample of a cosmological volume of matter. So that's exactly what we do to study fgas. You see here that it's this fraction should be then proportional to the baryonic density of the universe over the total matter density to the universe up to some factor called the baryon depletion factor, because as clusters form, they eject small amounts of gas. So the basic idea of constraining cosmology with fgas, well, you can do it two ways. First, we have excellent priors on omega B from Big Bang nucleosynthesis or the cosmic microwave background. And so then if we measure fgas, we get omega M. So this was first done in 1993. Actually, it was the measurement that showed that omega M is much, much less than 1. So we think there's something else in our universe other than matter. For many, many years, people thought most of the energy of the energy density of the universe came from matter. So that was a major discovery in 1993, done with this measurement. So the other way to constrain cosmology from this measurement is to think about fgas as a standard quantity. So basically, in late stage formation of these clusters, fgas isn't really changing. The gas isn't really leaving the clusters because they're so big. To get the energy to leave the cluster, it has to be huge amounts. And so for the largest clusters, fgas should be constant with respect to mass and redshift, so with distance from us. However, when we measure fgas, this measurement actually depends on how far away the cluster it is from us. So we have to model some cosmology into it because distance depends on cosmology. So we say, well, we know fgas is supposed to be constant, but when we measure it, depending on our model, it may or may not be constant. So we can constrain our model based on this principle. So this is exactly what we see in this figure. We have a fgas versus redshift for two different cosmology models. And this is pretty extreme. One is for omega m equals 1, and then no dark energy in the universe at all. So all the energy is in matter. We know this is wrong. So it looks very not constant. However, for a model that's very close to what we've been measuring, where we have omega m is 0.3, omega lambda 0.7, it's very flat. So this is an extreme example, but you can imagine then more subtle things where you try to really fit this and constrain this more precisely. And so in this way, we can constrain two quantities really well. We can constrain omega m, the matter density of the universe, and then W, the dark energy equation of state. So how do we measure this quantity? So we want to do so. Typically, you can just measure any galaxy cluster and say, we'll measure the mass of the gas, we'll measure the total mass, and then we can constrain cosmology. But we want to do so in a way that's very careful and to reduce systematics. So we choose the largest, hottest galaxy clusters that are relaxed, which means they're not undergoing any mergers. This is great because they're very spherical. That means the gas in the clusters is easy to model. It's not doing some fancy non-equilibrium process in a merger. It's really been sitting there for a long time. It's virialized. So that's what we're trying to measure, because it's will reduce our systematics and make our modeling as easy as possible. So we've taken the Chandra archive of all the galaxy clusters that they've measured and said, okay, let's look at their morphology and have some automated way to pick out these relaxed clusters. And so you basically look at the gas profile and you find the ones that are most symmetric, the ones that have strong peaks in the center, and that are very well aligned. And so this is called the SPA code, and we have an automated way of finding these relaxed clusters. So once you have your cluster sample, then you can measure fgas, and we measure this using X-rays. However, to measure the entire mass of the cluster, you then have to assume hydrostatic equilibrium. So another thing I should mention is when you do these X-ray measurements, you could measure the entire cluster, but the center of the cluster can have all kinds of complicated processes going along. So this gives fgas a lot of scatter. So we choose a spherical shell right at R2500. This is the radius at which the cluster density is 2,500 times the kind of average density of the universe. And so at this radius, then we have the lowest scatter. So that's where we make our measurement. Yeah.
Do we have an idea from simulation, maybe the fraction of clusters which are on isotropic equilibrium?
So it's a fairly low fraction. The number of clusters from the Chandra archive that is about 300 clusters that are relaxed is like 40. So it's a low fraction, but it's enough that we can get a lot of signal to noise on our measurement and very competitive cosmological constraints. And so the other thing I kind of glossed over is this baryon depletion factor. This is something that has a constant part and part that depends on redshift, but it is very well constrained by simulations. It's one of the most basic things that a simulation can measure. And we can even lower the scatter between different measurements and simulations because simulations all have different implementations by just choosing the spherical shell. And so here are very different simulations. This is a Planel's 2013, and this is, I can't remember this author. Anyway, it's another simulation, very different implementations, and these include extremely different gas effects. Some say that you don't have black holes. Some of them say there's no supernova. Some of them are just absurdly wrong. And even with these very different implementations, we find that the scatter is very low. And so we take a very wide prior. Yeah, so this is without the spherical shell. It's bigger, but then it's not too bad. And this is not the limiting part of our measurement. We're definitely limited by statistics. So as long as we're very conservative with this, we're not too worried. So I mentioned that we did all these measurements in X-ray, assuming hydrostatic equilibrium, but it turns out that's not quite true. Here is a simulated cluster where they made measurements of the gas mass fraction and the total mass, assuming hydrostatic equilibrium versus the mass from the hydro simulation. And you can see it's biased. Here it's 0.2, so this is like 20% in the residuals. That's a pretty big bias. We have another issue, and that is the temperature calibration from these X-ray satellites. XMM and Chandra are the two main satellites that take X-ray data, and they have a temperature calibration disagreement of something like 15%. And so that leads to uncertainties in the overall mass, which relies on the temperature. So we need some independent way to kind of resolve the fact that we're not in hydrostatic equilibrium and that there's some temperature calibration issue. And so that way is weak lensing. So one really great thing about weak lensing is it's completely agnostic to anything that's happening in the cluster. It just cares about how big it is. And so how does this work? If you have a very big object in your line of sight, it will bend space-time. So if you have light coming from behind the object traveling to us, as it travels, it will go through the bent space-time, and then the image that we get, that we measure with our telescope, will be distorted. Here's a picture of looking at some coffee beans through a wine glass. So it's somewhat similar. These coffee beans are kind of like faraway galaxies. The wine glass is like the galaxy cluster. And so you can see that the coffee beans, they have some shapes, but they're a little bit distorted from the wine glass. So we try to reconstruct the wine glass or the galaxy cluster mass by understanding how these coffee beans are bent. So you can see here, there's even some arcs. This would be strong lensing. That's something that we don't do. We do instead weak lensing here, where the coffee beans are just distorted a teeny tiny bit. And so this distortion is like a 1 to 2% effect per galaxy. It's really hard to measure for one galaxy, this signal. So we have to do it statistically. And so we do it over a whole sample of background galaxies behind the galaxy cluster. And so I just wanted to give a little timeline of this fgas measurement to show how it's been very important historically and where we're heading today and with this talk. So of course, I mentioned in 1993, we found omega m was less than 1 with this fgas measurement from the COMA cluster. It was then the second kind of cosmology constraint that I mentioned, where you could find fgas as a function of redshift, was done in 1996. In fact, the first direct confirmation that the universe was expanding at an accelerated rate that wasn't supernova came from fgas. And so in 2014, they really automated and standardized this pipeline to have relaxed cluster selection. They use a spherical shell, and so it becomes a much more precise measurement. And so in 2021, this was then constrained with additional X-ray data that they've had at very low redshift with the Perseus cluster and at very high redshift. So in this iteration, we're going to focus on mostly constraining omega m by doubling the weak lensing data set that will constrain or that calibrates the hydrostatic masses and will update the lensing methodology. So what is this weak lensing data set that we're using? It comes from 3 different telescopes. And so we have 40 clusters from X-ray that were determined to be relaxed. So we have data from Chandra. And so then we have some additional clusters that we viewed with these telescopes. So 8 were from the dark energy camera, 10 came from Suprime camera, 3 are from Mega Prime. These were all viewed with a number of wideband filters. So here, 6 filters, the others 5, and it's very deep targeted data. And so one of my jobs in my PhD was to go and observe these clusters at DECAM and do data reduction for DECAM data. And so here I am at DECAM. And so this is, DECAM is located at the Blanco telescope in Sao Paulo in Chile. It has a very wide field view, it's 2.2 degrees. The moon is like a half square degree. These wide field imagers can't just use one camera. They have a whole array of cameras. So it's 62 CCDs in an array. And so it's a 520 megapixel camera. So to take this data from the camera and go to a weak lensing cluster mass, we have to go through a few steps. So I'll tell you a little bit about the pixel level processing that has to happen, then how we take those cleaned images and make cluster mass measurements, and then finally how we do cosmology inference with all of these pieces. So a CCD, it stands for charge coupled device, and they exist in many cameras, and some phones have them, some use a different kind of chip, but it's kind of similar in process. It's kind of a digital form of film. And so an ideal CCD has these equal sized pixels with some linear response. So the signal you see in your pixel is proportional to how much light you got. It has a point spread function that is independent of how bright the light comes or the light is. So your object flux. So the point spread function is regular across the CCD. The only sources of light in your image are in the sky. They're astronomical sources of interest. So you don't have things like cosmic rays. You also don't have things like reflections from the telescope. The other thing is that the pixels are all on the same scale across the CCDs. However, real CCDs are very different from this, unfortunately. There's stray light from the telescope. There's some pixels that just don't respond correctly. So they're called bad pixels, and they are not holding charge. There's variations in the pixel response. So different pixels respond to flux differently. And there's all kinds of instrumental and atmospheric signatures that you need to correct to get an image that's good enough even to do the science that you want to do. So here's kind of a highlight of some of the pixel level processing we've done for DECAM data. So we've based this on the Tele pipeline. And so this is a very well-tested pipeline that was used for, say, kids data or CFHT lens data. But the problem with a very well-tested and well-used pipeline is that it's very old and it's built for very old infrastructure. And so this pipeline works basically on a glorified desktop computer. DECAM data is just not going to work on a glorified desktop computer. There's way too much of it. So we had to update it to run at a computing center. Here it was CCIN2P3. And also we had to update this pipeline to include camera specific corrections. So one is nonlinearity in the detector response. Crosstalk, so here's an example. If you have a very bright source in one CCD, the electronics kind of mix. And so this signal can appear in another CCD. So you have to correct for that. This so-called brighter fatter effect and stellar flat field, which I will then explain later. So the idea of the brighter fatter effect is that your point spread function, or how much a infinitely small point spreads as it goes through your instrument, this actually depends on flux. And this is because these are imagine these as individual pixels. And so the pixel walls are made basically with electric fields. And as you have charge that goes inside your pixel, it's going to bend these electric fields. And so then the wall of your pixel is going to shift a little bit. So if you have a lot of charge inside, suddenly this pixel will get wider and the pixel with a lot of charge gets smaller. And so that's a problem, because then really bright sources, the way the light spreads out will be very different from faint sources. And if you're measuring the shapes of galaxies very precisely, like you do for weak lensing, this becomes a problem because you can't do your calibrations correctly. So we had to do it. Yeah.
So this is an optical phenomenon and an electronic one.
This is an electronic one. So this happens in deep depleted CCDs. Any CCDs that have really deep wells for their pixels, the pixel boundary can change. So but the big issue is that we calibrate then with brighter stars to define our point spread function, but our galaxies are really faint. So if the point spread function is different for the galaxies, you can just throw it out. But the brighter fatter effect exists on any deep depleted CCD. And so the other big piece that we added to this pipeline was a correction for a stellar flat field. The pixel response to light is not uniform across the camera, especially for these wide field images. And so one thing people do is they take flat fields to try to even it out. And so they point the camera to one of these screens here that they illuminate in an even as possible way. So this is nice because it's very high signal to noise. But the problem is the spectrum of light that they use to illuminate the screens is not quite the same as the sky. Also, the light that they get is scattered. It's not this focused starlight. And you have to assume that the effective amount of screen that the pixel sees is the same for all pixels, whereas there's always some vignetting and geometric distortions. That means some of pixels get more sky, some pixels get less sky, depending on where they are in the camera. However, dome flats are really good for telling you the relative amount of light that each pixel is receiving. So on small scales, they do great. But because of this uniform pixel size assumption, they do very poorly on large scales. We also do a kind of flat field called super flat, where we try to take all of our images of the cluster and then take out all the sources, so there's just sky left, and we stack them. And we do this to try to correct the dome flat for some of these other effects. However, we still have this uniform pixel size assumption. So here's an example of a flat field that you can see for DECAM. So we correct this with a stellar flat field. And the basic principle is that a star has the same brightness anywhere it lives on your camera. If you measure it here or there, it shouldn't change. So you measure the same stars many, many times across the camera. And then you make some model for the response of the camera and say it had better be constrained by the fact that the starlight is always the same. This gives you about a 10% correction across the focal plane. It then doesn't assume this uniform pixel size, so you can correct for the fact that pixels in the middle see more light than pixels on the edges. And so here we see an uncorrected, I guess, our stars versus Gaia stars across the focal plane. And then here is, once you apply the correction, you can see it's very flat. So we were able to solve this stellar flat field problem. The other big piece that we put into kind of pixel level processing is our photometric calibration. So we have, I mentioned broadband filters. We have 5 of them. And you need to combine these filters later on in the measurement in different ways, which means you need to understand how, like, flux relative to each filter. So you need to make sure that these are all, if you have some flux in one filter, you can compare it fairly to the other filter. So this is an overall calibration on your images. So stars should follow some one-dimensional locus or 1D curve in color space due to stellar evolution. So if you take all your stars in your field of view, they follow this nice line. And so you can make a model for what this line should be, and then you can see how it is in the data, and then you just shift the 0 point of your data up or down so that the data will then match the line, and that will constrain your 0 point. So that's great. The only problem is for the bluest filters, this correction doesn't work anymore. And so this is because stars no longer follow this nice locus if you look at blue colors, because they vary a lot with metallicity. So then Shuang Liang and our group found a way to isolate stars with all the same metallicity. They live in the galactic halo, so that then you no longer have that metallicity issue, and you can then use stellar locus regression again. So now I want to talk a little bit about, once we have our nice cleaned images that we understand very well, how we can then measure weak lensing cluster masses off of these images. So this kind of involves a few processes. One is we have data that we read from these images. So we measure the galaxy shapes and we measure their photometry or how bright they are. From this data, we can then calculate shears and redshifts. Then we have a model. We assume a 2-parameter model. It's called a spherical NFW model. And this was a very common cluster model. And it's 2 parameters, so it's very easy to constrain. So then we fit the cluster, the data to the model using a method called the PFZ method. And that's kind of the 3 steps we do to do weak lensing. So how do we measure the galaxy shapes and photometry? So we have to first identify all the sources on the picture. So this step is catalog creation. We use a software called source extractor or Sextractor. We then have to characterize the point spread function. And here is the light as it before it goes through our atmosphere and telescope. But of course, once it goes through the atmosphere and telescope, it has been convolved by some point spread function. So we model that using a software called PSFX. Then we have to measure the shape of the galaxy somehow. So we fit a model, and this is a model fitting method called NGMix. We fit a Gaussian to this. And so that's how we measure the shapes. We also then integrate over this model Gaussian to find the photometry. Then from this, we need to calculate the redshifts. We use this software called BPZ, and I'll talk a little bit about redshifts in a moment. And the next part is to go from the galaxy shapes to shears. We need to do a process called shear calibration. So we use a process called meta-calibration, which I will also talk a little bit more about. And then finally, we do this final step of fitting the cluster mass. And so we do a method called the P of Z method. So when I talk about redshifts, what are we talking about? And how do we measure them? So galaxies have emission lines because there are stars with different metallicities or different forms of light that give these emission lines for each galaxy. And the light travels to us, and based on how far away it is, the light actually, the emission lines are all shifted in the spectrum in the red direction. So you can see a galaxy with different redshifts, and so its spectrum actually shifts depending on where you are. So it shifts towards the red as it comes to us. So normally you would then take your spectrograph and you measure each galaxy and you measure the spectrum. You'd find out how much the line shifted and you know the redshift. This is really expensive. We have thousands of galaxies. We cannot possibly do all the spectroscopy that we need to take our measurement. So we have to do the next best thing. So we measure, instead of taking all this detailed spectrum information that you see here, we use these broadband filters. And so these broadband filters then give you, instead of all these data points you get to make this plot, you get one data point for each filter, and you know the flux in each filter. And then we use a probabilistic method to try to then fit some template and find what the redshifts should be. And so, yeah, instead of these beautiful curves, you just have 6 points, but it's the best we can do. And so we did some tests of our redshift measurements to make sure they were accurate. So one thing you can do is, if you happen to have measurements from a spectrograph for a subset of your galaxies, then you can compare the what's called photometric redshift with these 6 points. And so here we have a very nice fit. It's noisy, but of course it's 6 data points. What do you expect? The other thing you can do is make a histogram of all of the redshifts right at the cluster, and you better see a peak where the cluster is at the cluster redshift. So here's for one cluster, we see indeed we get a peak redshift there, so we know at least the cluster galaxies are coming out the way they should. The other thing you can do is try to fit the cluster red sequence and then make a histogram of those galaxies. And so here we have an example of how horribly noisy this is, where we try to fit these red galaxies in color space and then make a histogram of those. So that's how we measure the redshifts. The other ingredient you need for this is the shears. And so you have to get the shears from the shape. So you've measured some shapes, they're ellipticities, but how do they relate to the gravitational signal that you want? So we use the old method actually comes from simulations. People would simulate a bunch of galaxies, they'd apply an external shear and try to figure out, okay, how can I recover this external shear from my simulations? And so that's what was done in previous iterations of this work, and many people still use simulations. The problem is you have to be able to simulate the universe very well. So you need to understand so many different galaxy shapes. You need to understand your instrumental effects. So you have to be very realistic. Also, you need a dedicated set of simulations per instrument. We have 3 instruments. We did not have the manpower to make 3 sets of simulations. So there's another method we could use called meta-calibration. This allows you to bypass the simulations because you actually re-simulate your image data. So you know that if you're taking all of your image data and calibrating with that, of course your galaxies will be representative of your sample. They're the same galaxies. And so this method is great because it's nearly unbiased. It's been used by the Dark Energy Survey for ensembles of objects and cosmic shear measurements. And it can be done for many different instruments. It can be done for many different shape methods. It doesn't really care. It's very agnostic to these things. So the idea is you apply an external shear to your data and you calculate this factor here called the shear response. Basically, what you need to know is the relationship between your gravitational shear and your measured ellipticity to first order is given by the shear response that we can calculate through this method, meta-calibration. So, okay, we first had data, which is our measured galaxies, and photometry. We processed it to get shears and redshifts. Now we need to fit this to a model and find the cluster mass. So the normal way that people would find a cluster mass is they'd say we have a redshift that we've measured, it's some number, it's a point estimate, and we can then put that into some weak lensing code that uses the lens equations to then fit our mass. However, this method has been shown to be biased. It's this method here in red. You can do better. So as you saw when we measured redshifts, we had this kind of junky probabilistic method where you have 6 data points, you fit some templates and you hope for the best. So it turns out this method returns more than just one redshift per galaxy. It returns an entire distribution. And so the idea with this method is then to use the whole distribution of redshifts instead of just 1 point per galaxy, so that you can understand then more of the spread and then get a more unbiased result. And that's what you see here in gray when we apply with this distribution. And it's even very robust to large amounts of contamination, as you see here. So the issue was, if we want to use this method, this takes information from every single galaxy. It finds its redshift, which is a distribution, and puts it in the lens equations. However, meta-calibration, our shear calibration method, works on simulations, and it's very, very noisy, and you have to find a sorry, I'm losing my train of thought. So, okay, we have single galaxy P of Z method that we want. However, meta-calibration has to be taken over an ensemble of galaxies because it's very noisy. And so how do we reconcile these two things? And so that's where we've made the new P of Z method. So basically what we do is, instead of putting shears into our lens equations to constrain our cluster mass, we put ellipticities. So we just forward modeled. So the quantity that I told you to remember before, the shear response, we forward model. So this is great. We no longer have to divide by the shear response per object, which is very noisy, which is a dangerous thing to do.
What is T here?
T is the size. And so we have this G here. It comes from it's the theoretical model. And this is the gravitational shear. E is our ellipticity. And then E intrinsic is the intrinsic shape variation of galaxies. And the nice thing is this is very, very wide distribution, much bigger than our gravitational shear signal. And so we don't have to do any kind of complicated noise modeling for this term here because it's so dominated here. So it's basically a Gaussian. So here is an example of us fitting a cluster mass. The axes labels are a little bit small, but we recover the mass, the concentration, which are the two parameters of the NFW model, and also the intrinsic ellipticity. So this is kind of a summary because I've said a lot of very technical things. Again, so we've started with ellipticity and photometry data. We've calculated redshifts for each galaxy using this probabilistic method. Then we've taken our ellipticities and we've calibrated them. And we've calibrated them using a method called metacalibration, which uses the images themselves rather than simulations. Then we are able to model our shear response and by fitting some polynomials, which allowed us to model our ellipticities. This then allows us to have our data, our model, and then we put it into the P of Z method to constrain our galaxy masses. So the last part of my talk is about how we put all these pieces together to do cosmology inference. So here are some results, the current fgas constraints from 2021, where we use the old method of cluster weak lensing. However, we have updated cluster sample. And so fgas here is in pink. And then this is compared to different probes. We have Planck, which is the cosmic microwave background. We have a supernova sample. We have baryon acoustic oscillations and 3x2 point. These are other measurements. And you can see that we are very competitive with these other constraints. This gray one here is not a super tight constraint on DES. It's a line at omega for lambda CDM. And so you can see that we have just 40 clusters, and our 40 cluster measurement is very comparable to some measurements that use huge pieces of the sky. The dark energy survey has something like 5,000 square degrees. And so just a little measurement can pack a very strong punch.
But you need also a big part of this kind to get these 40 clusters.
We do,
relaxed.
yeah.
You need also a huge area.
We do, but it's a very small team. I mean, DES has hundreds of people. You saw my list of collaborators, it's very small. So it's nice that this has so much constraining power, and we're still so statistics limited. If we had more clusters, we could really shrink these constraints. And so when I talked about using this P of Z method instead of some other methods with point estimates, we have put this into our cosmology inference pipeline, and we do have some preliminary constraints, but we're still blinded. So this is just for a subset of the cluster sample. But you can see we have constraints on omega M, which should shrink by about half in the future. And here's omega M and W is mostly constrained by the X-ray data. And so we have some improvements that we think we'll have on fgas in the future. And so this is kind of a summary of fgas through history. And so this is the from 2008, this is from 2014, and then this is the most recent version here in pink. And we expect then by adding this optical data that this omega M constraint will then go down by about a factor of 2. And so we're adding 11 more weak lensing clusters to the sample. We've updated to this metacalibration method instead of using simulations. And we've improved our cluster mass modeling, going from an old method that uses point estimates to this full P of Z method with metacalibration. And so this measurement has quite an interesting future because we are headed towards this golden age of observational cosmology. And I realize now that I've only put optical telescopes here, I'm highly biased, but there are other wavelengths that are also good that we should care about. And so here's Euclid, this is the Rubin telescope, and this is the Roman telescope. And Euclid's going to be launched July 1st. LSST, or the Rubin telescope, will turn on in maybe a year. And Roman is planned for several years from now, maybe 2027. But these telescopes are going to take unprecedented amounts of data across the sky. This data will be very deep. It will allow us to make many hundreds of cluster measurements. And so we will no longer be statistics limited. And so here's kind of the discovery space for some of these future surveys. So I mentioned optical there, but also there's X-ray missions. So eROSITA is ongoing right now. And so their discovery space, they're expected to find many more low redshift clusters and also lower mass clusters. So we're going to find many clusters in here. Here we have clusters that were discovered via the SZ effect. And so these were with CMB measurements from SBT. CMB stage 3 is ongoing right now. CMB stage 4 should be turning on in the next few years. So we'll be finding so many more clusters in this parameter space. Rubin will be able to look at this area, and Rubin plus Euclid, perhaps even these high redshift clusters. So the future is very bright. So if we have X-ray clusters out here, and then we're able to follow them up with these beautiful Rubin and Euclid weak lensing measurements, fgas definitely has a very bright future. And so here's some ideas of different ways you can projections for new constraints. And so if we were to have a very large Chandra survey of X-ray clusters, then we could perhaps shrink the current constraints quite a bit. And then for NXO, which is some kind of generic future X-ray mission, then we could shrink them even more. And of course, all of these can have beautiful optical follow-up with Euclid, Rubin, and Roman. And so I just wanted to summarize some of the things I talked about today. So the fgas test produces these really robust cosmology constraints that do not rely on a lot of underlying assumptions, and they constrain omega m, the matter density, and dark energy. And so, oh, this is an old version of this talk. So we have used lensing analysis to further calibrate X-ray measurements to constrain omega m. And we're preparing for cosmology with all of these new telescopes. So many of the methodology that we're using now is to work us up to this new golden age that's really about to happen. And so my contributions to this project personally include the lensing observations, pixel level data analysis, the mass pipeline, and the cosmology inference. So that's my talk for today. I hope that you learned something.
Thank you. Well, first, disclaimer that this is not my field level.
Yeah.
But I was curious when, so you said that fgas is expected to be constant also with the redshift.
Yeah.
And that's because the gas involved in galaxy evolution or star formation is negligible.
So there's lots of gas within the cluster as it forms, but gas is really only ejected from the cluster right at the beginning of formation. So that would be at very early redshift. So all the redshifts we're looking at, even probably redshift 1.5 on, the gravitational pull is so strong. But this is not just an assumption we pulled out of a hat. People have studied the baryon depletion in simulations as a function of redshift, and you can see, I mean, it's incredibly flat. There have also been other studies with simulations, Becker and Kraftsov, 2011. Many simulations have showed that that fgas is constant as a function of redshift.
Yeah, it's flat with the error bars on the right?
They are big, but they're so much smaller than the other error bars in this measurement that we don't care. So,
Another question here, yes.
Thank you for the talk. Very interesting. I have many questions, but I will ask the first one. I'm not sure how it's not clear to me how you include the omega lambda in your calculations. How to have discriminatory power towards that case.
so in lambda CDM, when there's no curvature, the sum of energy densities needs to be equal to 1. So if you have a lot of omega M, then you have, it has to come from somewhere, so that would be omega lambda. So you're constrained in this way.
So you assume flat, especially flat universe. The flat
You
ones.
can, we've also done with, we have constraints also with varying curvature. And we're still able to get nice constraints on omega M.
Because the last plot show us, it seems to be in tension with the flat lines. The previous one.
Sorry. Wait, yeah, they're up.
Yeah, I see more omega lambda, and more omega matter, and if you add up, if you sum up, then they're larger than one.
Let's see. I'm wondering if this has to do with, so I think omega lambda, when we constrain that, we do allow for curvature. So that would be why, because normally you wouldn't show it because it's completely constrained by omega M. So if we're plotting omega lambda, this is the case then with where we allow curvature to vary.
If you allow for curvature, then do you take into account the curvature in the weak lens? It could affect the.
So all the cosmology dependence in the weak lensing is put into the cosmology code. So we don't compute the mass with fiducial cosmology and then put it in the code. We constrain everything altogether. So, so it would be taken into account.
You have a question?
I also have one.
Yeah.
Go ahead.
Again, you pick the NFW profile, so you assume that the cluster is completely spherical.
Yeah.
What would be the effect if we allow for accretion? Because we see a lot of accretion across clusters, the source that perform the large scales.
So one nice thing is we've selected a very special cluster sample of relaxed clusters. So if there's large amounts of accretion, that usually occurs with when you have mergers. And so we can see in the X-ray data that they are very, very spherical. So triaxiality is a major issue with weak lensing masses. However, weak lensing masses have been shown on average to be unbiased. And so there have been simulation studies that have verified this. And so our sample is drawn from the X-ray sample, and they've done even checks on relaxed versus total population. And they found on average, the weak lensing mass is unbiased. So individual cluster masses are absolutely biased by accretion, but you assume that you have enough that it comes from different directions. And more statistics will only help this.
I have a question. So the pixel correction are quite intense, right? At the
Yeah.
beginning of the and you see all these effects that have to be combined. It's non-linear effects. It's very difficult to correct them. I was wondering if machine learning techniques could be helpful for steps, because then you can much better handle non-linear things.
Maybe. So a lot of these are taken from different calibrations they do on the CCDs in the lab, like they measure them by varying the temperature and things like that. So I'm not sure with a non-linearity correction, machine learning would necessarily be.
When you correct the flux, for instance, fatter or bigger.
The brighter fatter effect, though, that might be useful.
Really non-linear, right?
Yeah, no, the brighter fatter
Pixel
effect.
size and non-linearity.
Because what we have right now are electron models where we say, okay, this is how much the field changes with different amounts of charge. And so things will hop a certain amount, and then we unhop them by doing a convolution. So machine learning might be helpful there. But I'm not really sure the avenue that would be best in pixel level processing. Definitely for finding cosmic rays, machine learning is great for that. Or satellite masking, it's really good for that. So any kind of artifact that comes on the camera that's more transient, it's good. Or asteroids. But the nonlinearity is typically characterized in a lab, and they make models and then you apply it. So there's a lot of information that goes into it that machine learning might not be as helpful.
Okay, I have a last question. Is about this NFW profile.
Yeah.
So I remember times ago people were saying that NFW profile were not so accurate, and there are other profiles that we propose, like ionosphere profile. I don't know if you remember this.
Absolutely.
So does it impact the fgas measurement if you change the profile?
It shouldn't, because we cut out the cluster center. We say the cluster center is a hot mess. We're not dealing with it. You cut it out. And that's actually the only place where these different profiles diverge. So as long as you're in kind of this area that's not the full cluster at outskirts where you get gas clumping, and it's not the cluster center where you have all kinds of different gas processes happening, all the models are basically the same. So NFW is fine. And it's 2 parameters, so we can actually hope to constrain it. Too many parameters, weak lensing has a lot of trouble with. So we really cherry pick where we fit so that we know we can trust it.
Okay, any other question? Yes, go ahead.
So how do we expect clusters?
That's a good question. So I think even around redshift 1.5, relaxed clusters start to become rare. Around redshift 2, I feel like you're getting into proto-cluster regime. So I think the really young clusters people look at are much higher redshift than redshift 2, maybe 3 or 4. That kind of regime is really proto-cluster, so they're not relaxed at all. But definitely around redshift 1, there are still relaxed clusters, and that would be a great anchor for future measurements, especially Euclid. We can't measure weak lensing masses well to redshift 1 because our filters can't measure galaxy redshifts very accurately above redshift 1. So the background galaxies we can't constrain well, and we can't get rid of contamination well.
Okay. So if there is no other question, so thanks to you again. I'm still around for